right, welcome to the Explainer. Today, we are tackling a big one, distributed systems. We're going to break down how thousands of computers manage to talk to each other, and, just as importantly, how they're built to survive when things go wrong. So whether you're prepping for an exam or just need to get your head around this, you're in the right place. Okay, here's our game plan. First, we'll get into the core challenge of communication. Then, we'll look at the different ways systems can talk in groups. After that, we're going to demystify something called the Remote Procedure Call, or RPC. And finally, we'll wrap up with replication, which is kind of the safety net for this whole operation. So this is really the million-dollar question, isn't it? It's the puzzle that the entire field of distributed systems is trying to solve. And the very first piece of that puzzle, the foundation for everything else, is figuring out how these separate, independent computers actually talk to each other in the first place. And this visual right here, this says it all. On the left, you've got your tightly coupled system. Think of it like a team huddled around a single whiteboard. Everyone can see and edit the same space. That's shared memory. But on the right, that's our world, a distributed system. It's more like each person is in their own office with their own private whiteboard. To get anything done together, they have to pass messages back and forth. No shared memory. That one detail changes everything. So let's jump into our first section and really dig into that challenge. This whole no shared memory thing, it's the fundamental constraint that shapes every single design decision from here on out. I mean, think about it. When you're scrolling through Netflix or using Google, it feels like you're talking to one giant, all-powerful computer, right? But that's a clever illusion. What's really happening is you're interacting with a massive web of individual machines all working together. That feeling of a single coherent system is built entirely on a constant, frantic exchange of messages behind the scenes. So, if we know that message passing is the name of the game, what are the different ways these systems can have conversations? Let's break down the key communication patterns you are absolutely going to need to know. First up, the simplest of them all, unicast. One sender, one receiver. It is a direct point-to-point message, like a private phone call. Think of one server asking another, "Hey, do you have this specific piece of user data?" It's clean, simple, and direct. But what if you need to talk to more than one system at a time? Well, here's where it gets interesting. You've got multicast, which is like sending a group text message. You're not yelling at everyone, just a specific predefined group. Then you've got broadcast, which is more like making a public announcement over a loudspeaker. Everyone on the network hears it, which is powerful but can also be pretty noisy and inefficient. And now for the real chaos. Many-to-many communication. Picture a party where everyone is talking at once. It's tough to follow any single conversation, right? Same thing happens here. The absolute biggest challenge in this scenario is something called ordered message delivery. You have to make sure that everyone processes the messages in the correct sequence. If they don't, you can end up with some seriously corrupted data. Okay, let's zoom in now on one of the most common and powerful ways for one computer to tell another one what to do. It's a cornerstone of distributed computing, the Remote Procedure Call, or RPC. You know, an RPC is basically magic. It lets a program on one machine call a function as if it were running right there, locally. But in reality, poof, that function is actually running on a completely different machine, maybe thousands of miles away. The original program, the client, just waits. It's blocked until it gets an answer back. And to make this concept crystal clear, especially if you're studying for an exam, we're going to use a super simple analogy, ordering food at a restaurant. This maps perfectly onto the technical steps of an RPC. Let's walk through this. Step 1, you, the client, tell the waiter your order. That waiter is acting as something called the client stub. Step 2, the waiter writes your order on a ticket. That's called marshalling, packing up your request and its parameters into a format the kitchen can understand. 3, the ticket goes to the kitchen over the network. 4, the chef, our remote server, gets the ticket and cooks the meal. 5, the finished dish is brought back. And finally, 6, the waiter puts the plate in front of you. That's demarshalling, unpacking the result so you can use it. And here is what that whole restaurant scene looks like under the hood, in technical terms. You see the client on the left making a call. It hits the client stub, which packages everything up, that's marshalling, and gives it to the runtime system to send across the network. On the other side, the server stub receives the package, unpacks it, and hands the request to the actual server code to do the work. Once it's done, the whole process just happens in reverse to send the result back. So here is the absolute key takeaway. Highlight this, star it, remember it for your exam. Because the client and the server do not share memory, parameters can only be passed by value. You can't just send a pointer or a reference to some data. You have to literally copy the entire thing, package it up, and send the full copy over the network. Okay, so we figured out how machines can talk and give each other commands. But what happens when one of those machines just fails? Or what happens when a service gets so popular that one server can't possibly handle all the traffic? Well, the answer, and it's a huge one, is replication. Instead of having just one copy of your data or your service, you make multiple copies, or replicas, and you spread them out across many different machines. This is the essential safety net that keeps massive systems like Google and Amazon online 24/7, even when individual parts are failing. And really, there are two primary reasons, two huge drivers for why we do this. The first is reliability. Simple as that. If one machine crashes, no big deal. You've got other copies ready to take over. The system stays up. The second driver is performance. By placing copies of your data in different locations around the world, you can serve users from a machine that's physically closer to them, which makes things way faster and lets you handle a lot more traffic. So those two drivers, reliability and performance, lead directly to these four critical benefits you absolutely need to know. You get enhanced availability and reliability. Your system is just up and running more of the time. You get reduced latency. It's faster for your users. And you get greater scalability. You can handle more and more users as you grow. In fact, that reduced latency is often a key ingredient for achieving that scalability. But, and there's always a but, isn't there? Replication isn't a free lunch. It comes with one giant fundamental challenge. If you have 5 copies of the same piece of data and you update one of them, how do you make sure the other 4 get updated too? And what if 2 people try to update it at the same time? This is the problem of consistency, and it is one of the hardest problems in all of computer science. And that brings us to our final thought. In these massive global scale systems, trying to keep every single copy perfectly in sync at all times can be incredibly slow. This forces a fundamental trade-off. Do you choose strong consistency, where everyone always sees the absolute latest data, but it might be slower? Or do you choose eventual consistency, where things are much faster, but a user might briefly see slightly old data? There's no single right answer, and that very trade-off, speed versus correctness, is at the absolute heart of modern system design.